Hello everyone. This video covers sections 2.2 and 2.3 from the book. Just to refresh your memory, in the last section, in section 2.1, so recall that in section 2.1 we use the bisection method, okay, to solve equations of this form. So this is still the goal. In section 2.2, we're going to talk about fixed point iteration. So before we talk about fixed point iteration, well, we need to know what fixed point is, or what a fixed point is. So here's the definition. The number p is a fixed point for a given function if the value at that point is equal to just the point. The best way to think about a fixed point is this. Let's say that this is a function, and then y equals to x, or just p, is going to be this line, and wherever they cross, that will be the fixed point. Sometimes you could have more than one. Let's say that this keeps going, and then you have the line y equals to x, so you have a fixed point here and a fixed point there. Now remember that the goal we have is to solve f of x equals to 0, where f of x is a function. So therefore from here, if you write g of x equals to x minus f of x, if x is a fixed point, then this will give you 0. Okay? Now this is also equivalent to saying that f of x is equals to x minus g of x. Well, let's do a very simple example to explain what a fixed point is. Graphically, it should be obvious what it is. But let's say that g of x is x squared minus 12. So therefore, if you want a fixed point, then we need to solve gx equals to x. So this will imply that x squared minus 12 should be equals to x. All right, so then we can make this equals to 0. So from here, we will have the x squared minus x minus 12 is equals to 0. You can factor this easily. So the answer will be 4, and it will be negative 3. Therefore, the fixed points will be P1, it will be 4, and P2 will be negative 3. Now, clearly, if you do a graph, g of x, this will be minus 12. This is supposed to be a parabola. It looks like this. And then this will be the line y equals to x. And you can see that this will intersect when x is 4 and when x is negative 3. All right, so now let's look to Theorem 2.3. Theorem 2.3 says the following. If g is a function that is continuous on the interval ab, and then each value of this belongs to ab for all the values of x between a and b, then g has at least one fixed point in the interval ab. Remember that this is sometimes called the image of the function, so the whole image has to be between a and b. So this guarantees that you have at least one fixed point. Like here you have 2. Now you add an extra condition. If g prime exists in the closed interval ab, and there is a positive constant k, such that the absolute value of the derivative is less than k, which in this case means less than 1. So technically this is implying that the absolute value of g prime has to be less than 1 for all x that are between 0 and 1. Then you have a unique fixed point, or exactly one fixed point, if this condition is true. All right, so one more time, this is what the theorem says. Part A, or the first part, is obvious if the image of the function is between a and b. For all the values of x between a and b, then you will have at least one fixed point, right? So that should be obvious in the sense, let's say go from a to b, and if the image is also between a to b, then clearly one of the lines is going to cross through there, so you'll have at least one. Now, if the derivative exists and is less than 1 for all the values of x, then the fixed point will be unique. All right, so let's prove this part. Okay, you don't have too many proofs, but you do have to do a few proofs in this class. So here is the proof, and we're going to prove this by contradiction. So suppose there is 2 fixed points. Okay. And we're trying to show that this cannot happen. The 2 fixed points will be P and Q, where clearly P cannot be equals to Q. And remember, we are trying to prove this part only, that you have exactly a unique or one fixed point. So now, since P and Q are fixed points, that implies that G of P is equals to P, and also that G of Q is equals to Q. So this is what it means to be fixed points, right? So that's the definition. So therefore, by the mean value theorem from calculus 2, we have the following. We have the G prime for some C of is equals to G of P minus G of Q divided by P minus Q, where remember that P and Q both belong to the interval A to B, and C belongs to the closed interval A to B. Okay, let's try an example where we use the previous theorem. So the question is this: show the G of x, defined to be this, has a unique fixed point between -1 and 1. So the first thing we have to check is G of x continuous? And the answer is yes, because we're not dividing by 0. The domain of this function is actually all the real numbers. And in either case, we only care that it's continuous in here, so this is fine. Now, what about this? Is the image of G contained between -1 and 1? And this one is a little tricky to check, but it should be obvious that's the case in this sense. If G of 1 is equal, you can check that G of 1 is equals to 0, which clearly belongs to -1 and 1. G of 1 is equals to 0, which also belongs to to minus 1 and 1. G of 0 is actually equals to minus 1/3, which is also between minus 1 and 1. So therefore this is okay. That's not a rigorous way to show it, but that's a way to show that the image is in there. Then we find the derivative. G prime is equals to 2 over 3x. Now we find the critical value from here. G prime of x equals to 0. That implies that x has to be 0. So this will give you the maximum, but we already saw that the maximum value is this, which is also contained between minus 1 and 1. So far so good. Now what is the absolute value of the derivative? So g prime of x, or g prime for some c, okay? So g prime of c clearly is less than or equals to 2 over 3, because you're going between minus 1 and 1. So therefore this is always the case. Okay. This is a 4 any c that is between minus 1 and 1. So therefore this is less than 1. So that satisfies the second condition of the theorem. So therefore by theorem 2.3 that we just saw, we have, or we know, actually let me write like this, by theorem 2.3, that implies that there exists a unique, okay, so this is going to be the lazy way to write unique, and this there exists a unique fixed point, which for lack of a better name we'll just call it P, okay, that is between minus 1 and 1. And actually we can, it's not asking you to solve it, but if we solve that, we have p squared minus 1 equals to 3. This has to be equals to p. Remember, this is where g of p equals to p means. So from here we have the p squared minus 1 is equals to 3p, which implies that p squared minus 3p minus 1 is equals to 0. Now you cannot really factor this, so you use the quadratic formula. This will be 3 plus or minus the square root of 13 divided by 2. And notice that you had two fixed points, so p1 will be 3 minus radical 13 over 2, which is around negative 0.30, and this is the one just as promised. Now notice that there is a second fixed point, but this one is around 3.3. This is outside the interval, so therefore this is not contradicting the theorem. Notice the following, which is very, very important. For this fixed point, if we find g of 4, let's say that the interval we extended to 3 to 4. Clearly we have a fixed point between 3 and 4, okay? If we apply the theorem, this is what happens. G of 4 will give you 5, which is already outside the interval. But more importantly, g prime of 4, it will give you a over 3, and you should check this, which is more than 1. So therefore, these conditions mean the following. It means that this is sufficient, but not necessary. The point is that you can still have a fixed point even if it doesn't meet the conditions of the theorem. But if you meet the conditions of the theorem, you definitely will have a unique fixed point. Let's look to another example, like similar to the second fixed point. Okay, so remember, this is the second fixed point, which doesn't go with the theorem, but you still have a fixed point. All right, so remember that this is the same thing as 1/3 to the x. Now, if we're going to graph this, hopefully you remember that the graph looks like this. This is the number 1, and this is the exponential function that it goes down like this. Okay. Now, clearly, this has a fixed point. So you just draw a line, the line y equals to x. So clearly this has a fixed point. That is obvious. Okay. Now, if we consider the interval, let's say from 0 to 4, okay, then clearly g is continuous, and the image is actually between 0 and 4 too. You can see the maximum value you can have here is 1, so therefore all of these values are less than 1. So clearly they will be between 0 and 4. But notice that g prime of x is equals to -3 to the minus x times ln 3. And then g prime of 0, it will be -3 to the 0 power times ln 3, which is equals to minus 1.09. Obviously, the derivative is bigger than, or is not less than or equals to 1. So the derivative for all the values between 0 and 4 clearly is not less than 1. So therefore, this doesn't meet the criteria for the theorem, but clearly you still have a fixed point. So that's obvious. But then you still have a fixed point. Okay. Which is what this part is saying here. That is sufficient but not necessary. So this definitely applies in here too. All right, so let's see how fixed point iteration actually works. It's very, very simple, the process. You start with an initial approximation, P0, and then you're gonna create a sequence of approximations, like P1, P2, P3, all the way to infinity. And this is technically the process. Now, whatever you pick for G, this is gonna be very important. So the choice for G of x is going to be very, very important. And if it meets the qualities or the conditions of theorem, the last theorem we did, then it will converge. If not, it still may converge, but your chances are pretty low. Now, we saw this example before, and this can be written in this form. So there's actually a fifth way to write it using algebra. So in theory, all of them are the same. Not in theory, actually they are the same. However, you will see that the different values of G will have different effects. For example, this is the most lazy way to do it. So let's say that the initial condition is 1.5. So therefore, for P1, it's going to be G of P0 for this case. So for this particular case, this will be equals to 1 minus 1.5 Q minus 4 times 1.5 squared plus 10. And you should check that this is equals to minus 0.875. The exact solution to this, so the exact solution is actually 1.365230013. Now this one is not that bad yet, but let's see what happens in the next approximation. So P2 will be now g of p1, which means it will be minus 0.875 minus 0.875 q, and so forth. Okay, this is a square plus 10, and the answer to this is 6.732, which you can see is now completely off than the exact solution. So clearly this is not your best bet to solve this problem. Now I'm just gonna show you how we got the rest, but you're gonna repeat this process using these functions. So for example, for this one, to get part B, you have this xq plus 4 x squared minus 10 is equals to 0, right? So technically you can do this. This is just you just have to play with the algebra. This means that xq is equals to 10 minus 4x squared, or if you divide both sides by x, you will have the x is equals to 10 over x minus 4x, and therefore x will be equals to the square root, or plus or minus this, but we want to go with the positive side. That's it. So if you use algebra, this is how you get all the different versions of g. All right, so this one, this is how we get this one, and if you do more algebra, you can get the rest. So to get this one, you can do this. You can have 4x squared is equals to 10 minus x cubed, or x squared is 10 minus x cubed over 4, and then you take the square root. X is going to be 1/2, because the square root of 4 is 2. 10 minus x cubed to the 1/2. So that's how we get these functions. Now the reason why we're doing this is because we were trying to find some function that it is continuous in the interval and that it satisfies the theorem. And by that, remember, the derivative is less than 1, then you will have a unique fixed point. All right, the following table represents the values, or summarizes the values that you will get if you use 5 methods. I only have the first 4 equations here. So you can see this value is this one, this is the second one, and so forth. So you can see that this one is completely off the rails. It has no hope. This one is also pretty bad. You end up with a square root negative value, which is a no. Part C is better, and you can see part D is definitely better. The best one is part E, which I didn't write here, but it's in the book if you want to see it. So the point is, the choice you have for the iteration is going to make a big difference. Now you should check some of these values yourselves. So for example, let's say that if we use this value, we're going to start, or this form, we're going to start with P0 equals to 1.5 again. So therefore P1 is going to be G3 or 1.5, which should be 1/2 times 10 minus 1.5 Q, and then the square root of everything. And you should check that this will give you 1.28695376A if you use that many decimal places, and so forth. So then P2 will be G3 of P1, and that should give you the next value, and so forth. All right, so now let's look to Theorem 2.4. Notice that the first part is the same same wording of theorem 2.3. So the theorem says the following: let G be a continuous function between A and B, and the image be also part of A to B for all x between A and B. In addition, suppose that G prime exists and is between 0 and 1. So remember, this guarantees that you will have a unique fixed point. So now the next part says, then for any number that is between A and B, then the sequence defined by this, which is the iteration or fixed point iteration, converges to a unique fixed point where, a unique fixed point in A to B. Again, it has to satisfy these conditions, which if you look back to the methods we have A, B, C, D, the first one doesn't satisfy this, so that's why it doesn't converge. The proof for this one is also pretty interesting and very useful to know how to do it. So before we go to that, so note from the past. So note, when we say convergence, it means this. So if Pn converges to P, that means in this case that G of Pn minus 1 converges to P. Because remember, the iteration is this: Pn is equals to G of P of n minus 1. Okay? And another way to write this is that the limit at n goes to infinity of Pn minus P is equals to 0. So this is what you want. So this is what converge means in this sense. All right, so we start with the absolute value of this. This is the approximation. P is the fixed point. Again, if we use the mean value term, so remember that this means this. Notice that if this is the fixed point, so therefore that's why G of P is exactly equals to P, because that's the unique fixed point you're trying to get. But the iteration says that Pn, the approximation, is equals to the previous value evaluated at the function. So by the mean value term, this will equals to G prime. So this is the same as the proof we did right now, times this will be Pn minus 1 minus P, where Cn is between A and B. Okay. Then since the derivative is always less than K, this will be less than or equals to K times Pn minus 1 minus P. Okay. So again, remember that this was by the mean value term. Now, if we do this one more time, and by one more time I mean this. Notice the similarity between this and this. So you do this one more time, this is going to be equal now to, or less than or equal to, this will be K times, this will be now K times P n minus 2 minus P. So this part will give you this if we go through the iteration one more time. Okay, so therefore this is equals to K squared times P to the n minus 2 minus P. Now this is the case if you do it twice. So if you do it n times, this will be less than or equals to K to the n power divided by P, times the absolute value of P 0 minus P. Now before we take the limit, recall this from calculus 1, that the limit as n goes to infinity of any number to a power, as long as the number is less than 1, that this is equals to 0. Here, remember that the value for K is between 0 and 1. That's what the theorem says. right here, right? So therefore, from here, the limit as n goes to infinity of the absolute value of Pn minus P is less than or equals to the limit as n goes to infinity of k to the n times P0 minus P. But based on this part is going to be 0. So this part will goes to 0. So then this will be 0. And that implies, using the definition from here, that the sequence will converge. The Pn equals to g of Pn minus 1 converges to, so this means converges to the fixed point, P. There is an extension to this theorem, and that will be corollary 2.5, and this one has the bound in terms of the first two approximations. So this one tells you that the difference between the approximation and the fixed point has to be less than k, where this is related to the derivative of g, okay? And you multiply that times the difference of the two first approximations. And this one is related to the initial approximation times the endpoints of the interval. So the proofs for this are very similar to this one. So if you are bored and you have nothing else to do, just give it a try to this one. All right, let's go to section 2.3 now, which is called Newton's method. You saw, or hopefully saw, Newton's method in Calculus 1. Obviously not to the same level we're going to look at it right now, or the same depth, but this is the exact same method from Calculus 1. Now here we have the actual algorithm, and notice something very, very important, the connection with the previous section. Notice that the value of n depends on the previous value. So technically this is a type of fixed point iteration. By that I mean this: you can technically write Pn is equals to some function g that is evaluated at the previous point. So therefore this is a fixed point iteration. Now the derivation of this algorithm is actually very, very important. It's pretty straightforward, and not only is going to be important for now, it's going to be very important in many things we're going to do later. Now, to derive the algorithm, we need to go back to something you learned in Calculus 2. We talked about this in one of the previous videos. Remember Taylor's series or polynomials? Okay. So by definition, a Taylor polynomial of some function f of x, remember, what's the sum from k equals to 0 to infinity, so that's the series, of the k derivative evaluated at some point, let's say a, divided by k factorial times x minus a to the k power. Or if you expand it, this will be equals to f evaluated at a plus the first derivative evaluated at a times x minus a divided by 1 factorial, which is 1, plus the second derivative evaluated at a times x minus a squared over 2 factorial plus, and then it keeps going. Remember that the goal has been in chapter 2, or the goal of chapter 2 is to solve f of x equals to 0, or in our case, f of p equals to 0. So don't forget that that's the goal. So therefore, if that's the case, then we're going to use this expansion, okay, and we will have the following. 0 is around f of p 0, so the value for a is going to be p0, which is the initial approximation, plus f prime evaluated at p0 times x is going to be p minus p0. And we are not going to use this, so we're going to cut it in here. So this will be the truncation error that we talked about before. Now, if we do a little bit of algebra, we will get the following. We will have the f prime of p0 times p minus p0 is approximately equals to minus f of p0. So technically just move this to this side and then just get this. All right, so now if we divide by f prime on both sides, we will end up with p minus p0 is minus f of p0 divided by f prime of p0. And then if we solve for p, remember that p is the fixed point, then this will be p0 minus f of p0 divided by f prime of p0. Therefore, from here we can create the algorithm, and then we will have the iteration. The fp of n will be pn minus 1, the previous value, minus f of pn minus 1 divided by f prime of pn minus 1, which is the original thing I gave you at the beginning of the page. Now, again, to make the connection between this and what we did in the last section, you could also write it like this. You could say the g of p of n minus 1 is the same thing as p of n minus 1 minus f of p n minus 1 divided by f prime of p n minus 1. Now, this is a graphical representation of how the method works. Remember, this is the initial approximation. Then the method is going to give you p1 somewhere here, where this is related to the derivative. You can see you start here, p1 will give you here, but then when you go to p2, it's getting closer to this. So eventually we'll get to the actual fixed point. So Newton's method has some advantages and some disadvantages. I will point out in the next page. But the main advantage is that if you start close to the solution, then this will converge pretty fast. So the convergence of this method is better than the secant method. All right, let's do an example to see how this works. Here, remember that f of x equals to 0 for this is telling you technically what's the square root of I, which is around 2 point something. I think it's 2.23. Okay, and it has more digits. So therefore, you already know the answer should be around that. So here to start, we're gonna say, okay, pick the initial condition equals to 2. So this has to be given, otherwise you cannot start the problem. All right, so here we also have the f prime is equals to 2x. Therefore, p1 is gonna be equals to p0 minus f of p0 divided by f prime of p0. So in our case, this means that p1 will be equals to p0, which is 2, minus f of 2 divided by f prime of 2. And in our case, p1 will be 2 minus f of 2 is 2 squared minus 5, which is negative 1. And f prime of 2 is equals to 4. So technically this is equals to 2 plus 1, 4, which is 2.25. So in the same way, P2 will be P1 minus f of P1 divided by f prime of P1. So in this case, this will be 2.25 minus, you should check this is 1 over 16 divided by 4.5, and this is around 2.361. So you can see that the answer is very close to the real one. That's not surprising because the initial guess is very close to the actual solution. All right, so let's try another example. So now the function we're trying to solve is f of x equals to cosine x minus x. Here, the initial condition or the initial approximation, they tell you to use pi over 4, which is equals to 0.7853981635, which is technically this one right here. We need the derivative. Remember the derivative for f, it will be minus sine x minus 1. So therefore we use the method, and P1 will be equals to P0 minus f of P0 divided by f prime of P0, which in our case, this will be pi over 4 minus cosine of pi over 4 minus pi over 4 divided by minus sine of pi over 4 minus 1. And this will be very, very tedious to do by hand. But once you simplify this, you actually get 0.739536133. So you should check on that, and so forth. So the table on the right side right here is giving you the value. So this was the initial condition. So this is just a pi over 4. So this is P1, the value we just found right now. Then you will have P2, P3, and so forth. Notice that these two values are the same, which means this is getting very closer to the actual solution, which this is very close to the real thing. Now this table was created using one of the previous methods. I don't recall if it was the bisection or the fixed point iteration, but in neither case, this is the solution, which it only took like technically 3 steps to get there. Well, this one after 7 steps is not even close to being here. So the point is that Newton's method has the advantage that is very fast if you start close to the solution. So the advantages of this method is that it is fast. When it works pretty fast. But it has some disadvantages. And the main disadvantage is that P0 needs to be close to the solution, which you may not know what the solution is, so then you'll be in trouble. And the other disadvantage is that you need to compute f prime of x. And this is actually a huge disadvantage because you may not have it, and if you want to compute this, f prime can be very costly, and costly in numerical analysis means that it takes a lot of computation time. So because of this, Newton's method is not very, very efficient in that sense. You don't have the derivative. The Newton's method is you have to first approximate the derivative, and that's going to create issues because now you're going to be using an approximation to approximate something else. Alright, so let's look to the next theorem, which says the following. if f is a continuous function with two derivatives, and then p is between a and b, such that p is a root of the function, and if the derivative is not equal to 0, then there exists a delta such that the Newton's method will generate a sequence from 1 to infinity, that should be infinity, converging to p for any approximation. Now, the proof for this one is very interesting too, and I think it's one of the homework questions. The key is that you need to use this. I believe the book has it too, but this is what you need to use to prove this theorem, which, as you can see, this is clearly Newton's method. So just give it a try, and I believe this is one of the homework questions, and you can ask for help in this during the office hours or during the Monday class. Now, before we go to the next page, like I point out here, the main disadvantage of this method is that it requires to compute the derivative. So in the next page or the next slide, we're gonna modify Newton's method so it doesn't require the derivative, because this again may not be easy to find, or if it is, it will be too costly to approximate. Now, before we look to the secant method, just recall from calculus. Remember, by definition, f prime is the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0, or the limit as h goes to 0 of f of x plus h minus f of x divided by h. So therefore, instead of using the actual derivative, which will be this limit, we'll just use this, which is the slope. And once we substitute this for the derivative, you will get this formula. So I'll show you how to get in a little bit. But this is technically Newton's method modified when the derivative is replaced by just the slope of 2 points. Now let's go back to the calculus definition. The first one, let's call this a star. So therefore, by definition, f prime, let's say, of p of n minus 1, the actual derivative, should be the limit as x approaches to p n minus 1 of f of x minus f of p n minus 1 divided by x minus p n minus 1. Now, if p n minus 2 is close to p n minus 1, okay, so this is a if. So if this is true, then we can say the derivative of p n minus 1 is just approximately equals to the slope, which is what I just told you like 5 minutes ago. So then this will be just the slope between those 2 points, p n minus 2 minus f of p n minus 1 divided by p n minus 2 minus p n minus 1. But remember that Newton's method was this: p n was equals to p n minus 1 minus f of p n minus 1 divided by f prime of p n minus 1. So what we're going to do is we're just going to substitute this in here. So if we do that, then from here we will get p n is going to be p n minus 1 minus f of p n minus 1 times p n minus 2, actually p n minus 1 minus p n minus 2 divided by f of p n minus 1 minus f of p n minus 2 once you watch out for the signs. Which now this will be the secant method, which is how we got this formula right here. Alright, so now we use this method to solve the problem we did before. Remember, we have x squared minus 5 was equals to 0. But now we're going to require two initial points. So let's say that p0 is 1 and p1 is equals to 2. Therefore, p2 is going to be equals to p1 minus f of p1 times p1 minus p0 divided by f of p1 minus f of p0. So in our case, this will be 2 minus f of 2 times 2 minus 1 divided by f of 2 minus f of 1. And once you simplify everything, this will give you 2 plus 1/3, which is 2.3333, so forth. All right, so now the table on the side is for the function cosine x minus x. So these are the values you will get. This is using Newton's method, which is the same table we did before, and this is using the new method. So notice that the secant method is always going to require two initial conditions instead of only one. Otherwise, you can you won't be able to do the problem. And also notice that this Newton's method in theory is supposed to be more accurate, because this one is using the actual derivative, while this method is approximating the derivative to use it in the method. Okay? And that's technically what the graph shows you here, that now instead of using only p0, you're going to need p0 and p1 to approximate the p2. So you will need p0, p1 to find p2, and then just keep it going that way. So you're always going to need 2 points instead of 1. And I believe that's it for 2.1 and 2.2 and 2.3.